So we're going to go from where we were talking before, which was decision making under uncertainty using Markov decision processes. What we saw before was really good if you've got a long time to think or a really big computer or a simple problem. When we move these things to robots or embed them in the real world, we tend to not have access to that. So instead we solve it with algorithms like Monte Carlo Tree Search. And those are things we can run for any amount of time and get better solutions as we go. It's probably best to go back and remember the previous couple of videos. So we started off by talking about modeling decision problems using Markov decision processes. And those decision processes capture the states a system can be in. They might be locations for a robot, and the uncertainty that happens when you transition between states via actions. And we had this slightly sort of toy example, but we're going to carry on using it because it saves us inventing a new one and explaining another one, which was commuting. So I'm at home and I can choose to go via my bike or via car or via train. And then there's different probabilities of taking particular durations to get to work. And we're looking to solve that model. And that's just an example of a Markov decision process. We want to solve that model for some objective. And the objective we looked at last time was minimizing the average time or the expected time. And we did that last time using an algorithm called value iteration. So value iteration looked through all possible states, all possible actions, and incrementally computed the optimal values for all states and all actions. So it's an optimal algorithm, and it required access to this model. So the MDP model itself has states and actions, and we write down transition functions. Those transition functions capture the probability of moving to that next state. And the models we saw before assume someone's given you this big text file that has all those probabilities in them. And then the algorithm, enumerates these, so lists all actions, all states, and you get these really big matrices. And I think we ended the last video by talking about the computational complexity of the algorithm. And it was kind of quadratic in the number of states, and the amount of memory you need gets very big very quickly. So in practice, those algorithms are really useful for certain classes of problems. But my research is in robotics and in decision making for systems that are typically mobile or embedded in the real world. And that real world is dynamic and it changes. And you want your systems to make decisions quickly as the world changes. So what that typically means is because it's the real world, we don't always have the ability to write down that MDP model. So it's very hard to actually get that text file with all the probabilities in it. And then the other thing that's the problem is the thinking time. We can't just sit there and think for as long as we like until value iteration is run, or we don't have access to a supercomputer to put on our little mobile robot. So we have to do something else that takes into account the real-time dynamics or the resource constraints of the platform.
Somebody commented that there was no way that your cycle had 100%. I know it was a toy example, but what if you got a puncher, I think, pops up?
Yeah, exactly.
You know, that's the real world, right?
That's the real world. Although all of the algorithms we're going to look at, well, the algorithm we look at today and all the algorithms we'll look at in the future, if we do more of this, will struggle with dealing with very low probability outcomes. So the model we saw before, you could just add another outcome of like puncture probability 0.0001 or something, and that would be factored effectively in. Because if I know that probability, the model-based approach that we had can use it. But yeah, I mean, all of these that's a good point. All of these probabilities are approximations of the real world, and you want to make your approximation as accurate as possible. When we do this in real robots, we typically learn that from data. We need to move beyond these two constraints, kind of assuming effectively unbounded thinking time, and having the model and having to enumerate all the states. So there's a kind of class of algorithms that we can use that don't have these limiting assumptions. And they are typically tree search algorithms. So in previous Computerphile videos, I think we've seen kind of shortest path algorithms, A*, things like that. Those are tree search algorithms. They assume that you have access to a model, and they use that model to expand the tree to find the path to the goal. But those tree search algorithms are great, and they're great for robotics because they assume you know the initial state. They assume you know where you're starting from. And if you know where you're starting from, you don't have to go through this process of enumerating all states. You can just start from the state I'm in and look for a route to the goal from this current state. So that immediately just reduces the amount of complexity or the size of the problem. But they don't have this property of that you have to run A* until it's done. Basically, you don't get to think for as much as you want, and it still assumes the model. So we're going to start looking at tree search algorithms to reduce the state space. But the other thing we're going to look at is something called sample-based or trial-based algorithms. So these are algorithms that instead of assuming you have this full text file with all the probabilities, all we assume is what's called sampling access to the transition function. What that means is instead of it giving me the probability distribution, what it does is I give it the state I'm in and the action I want to take, and then it gives me back the next state that I reach this time. So we sample just one sort of instance or one realization of that uncertainty. So it's just like rolling a dice. When you buy when you buy a die, it doesn't have the probabilities listed on it. You roll it and you get a 6 or a 4. If you want to actually sort of back out the probabilities, you have to do that a large number of times, and then you know the probabilities. And so that's sampling. It's actually it's effectively rolling a dice, tossing a coin, drawing. We often call drawing a sample. I'm going to draw a sample from my distribution. And when I've got a simulator, and that's kind of a simulator in inverted commas, it doesn't have to be like a video game like world or some complex thing. Generally, we just think that as a way it's simulating the dynamics. We just sample from that simulator, it gives us the next state. And that is a much less restrictive assumption, typically, than assuming we have the full model. So we're going to look at these tree-based algorithms. They're going to use sample-based planning or trial-based planning, so sampling from a distribution rather than having the model. And we're going to switch mode a little bit from thinking about offline, what we call offline planning, and then online execution. So previously, our offline planning phase created a policy, and we executed that policy online. We're going to now interleave planning and acting. So our planning process is going to happen before we act, but we'll think about it as happening before every action rather than the whole mission or the whole plan. So we're going to run a short planning phase. That planning phase is just going to tell us the next action to take. Then we execute that action and we think again. And what we're going to do in the algorithm we're going to look at, we can think for actually as long or as short as we want. The longer we think, the better the answer, but we can actually take our answers fairly quickly if we want. So those types of algorithms are called anytime algorithms because you can run them for any time, and you are guaranteed if you run them for longer, the solution doesn't get worse. It may not get better, but it doesn't get worse. That's a simple condition to sort of get, but your algorithm has to be structured to allow that kind of anytime termination. This class of algorithms, these trial-based tree search algorithms or sample-based tree search algorithms, there's a bunch of them. Perhaps the most famous is one called Monte Carlo Tree Search, and that's the algorithm we're going to look at today. And we're going to look at a particular instance of it called UCT, which stands for Upper Confidence Bound Applied to Trees. And that'll be a bit of maths we use later, but we can come back to that. So Monte Carlo Tree Search, one of its most famous recent applications was in the AlphaGo system that DeepMind built to play Go. It used Monte Carlo Tree Search to explore the game tree of Go. But it's really widely used in robotics and other AI applications. Mm-hmm. So Monte Carlo Tree Search does two things. It incrementally builds the search tree. And it does that in a trial-based fashion. So rather than just in one pass expanding the tree, we're going to run trials. A trial starts at the root of the tree, and it goes down the tree until the trial stops. And each time we go down, we're going to more or less add an extra node to our tree. So we're going to grow our tree node by node, one node per trial. And so we're gradually building the tree. We're also gradually estimating the values of our actions. And if we think back to the previous videos, we've got our state values, which is kind of how good it is to be in the state, and we've got our Q values, which is how good it is to take the action in that state. And the state value is defined by the best Q value. But we don't know those. We haven't got them in our model. We can't calculate them directly using the Bellman equations that we had before. Instead, the Monte Carlo method samples values of these values. So we get instances, we get a little bit of information, and we're going to then just take averages. And that's what the Monte Carlo method is. So Monte Carlo appears in all sorts of different places in terms of optimization, in terms of sort of calculus and all sorts of stuff. We use it this is effectively Monte Carlo statistics, where what we're doing is rather than doing something in a closed form, we're just drawing samples and we're averaging the samples to give us our estimated value. So typically we're using sample averages, that's what they'd say in statistics, and that's the Monte Carlo method. Draw some samples, take an average. The problem with that is you can be very biased or very wrong depending on what samples you draw. So today I'm going to be very optimistic and draw the samples that tell a good story, but it's the kind of algorithms we're looking at are very, very prone to bad initializations. If you get a couple of bad samples to start with, you're going to really make some bad decisions in a kind of finite time. The thing about Monte Carlo, the reason it's nice, is in infinite time, I get the right answer, guaranteed. But we never have infinite time. And I'm probably running late already, so I shouldn't do this for infinite time. So there's a couple of stages to the Monte Carlo Tree Search algorithm. Each trial effectively runs through selection, which is going to be going through the tree. We're going to work from the bottom of the tree, selecting actions until we get to a leaf node. When we get to a leaf node, we then expand. Expand is adding that next node to the tree. But the problem we have, because we don't have the model, we don't know how good that action is. So the way we deal with initializing that node that we've expanded is we then simulate. And that simulation involves using we're going to use our sample access a lot, but the simulator is more or less going to take a bunch of random samples through the tree to simulate what might happen when we plan further in the future. So often you hear people talking about rollouts in AI or RL, and this is what we're going to do here. We're going to use random rollouts through our tree, and then we're going to do the backup. So that takes the results of all of our expansions and simulations and sends the values back up the tree. So we're down the tree, we've got values at the bottom because that's where we've been doing our expansion, and we're going to back the values up the tree, which is going to sort of trickle back up the tree until we finish our trial, and then we start again. So this is where the trial starts, and then we loop this as many times as we want.
So that's your potentially infinite times, but hopefully not.
Yeah, indeed. So, and you do this, until you run out of time. So a lot of the textbook will say, while thinking time remains, and then just like abandon that to other things. I could talk about that for ages. Mm-hmm. Let's get on to algorithms and see how this goes. I'm going to start with our tree, and we're going to use the same example as before, so this commute example. And we know our initial state, so I'm going to put our initial state at the top of the page. And this is going to be the state of home. Our first trial requires us to expand, to select to start with, but we've got no actions, there's nothing to select. So now we actually have to expand the tree by adding a node. And in the home state, we have three actions we can take. In alphabetical order, we can go by bike, we can go by car, or we can go by train. We can walk to the rail station. One of the key parts of Monte Carlo Tree Search, the thing that makes it UCT, which I answered before, is the way that you select actions in the tree. So actually, I'm going to jump to another bit of paper just to explain that. So we've got a choice of actions, and if we knew everything about the tree, we've been running for like an infinite number of times, or a very large number of times, then what we'd do is we would choose the action that minimizes our Q value. This would make sense if I had this full model, if I'd enumerated everything. But the problem is we're incrementally building the tree. So if I choose some action that minimizes the Q value, that Q value might be wrong because I might have only taken a few samples, a few trials through my tree. So this might be inaccurate, it might be biased because I've drawn some bad samples, like some unlikely samples. And so this is not necessarily a good way of representing the value in the tree. And it reflects the fact that we haven't explored the tree. So this comes to a key trade-off that you see in a bunch of decision-making algorithms and a bunch of learning algorithms, which is exploration versus exploitation. So explore versus exploit.
So sort of like find something out rather than do.
Yeah, and these things are really coupled. So if I exploit something without exploring alternative options, how do I know I'm exploiting the right thing? But if I spend all my trials, all my time exploring, then what I might be doing is wasting time looking at things that aren't good, and I'm also not making any of my individual estimates better. So, for example, if I run one trial and it says this is a brilliant action, I could then just kind of assume that's good. But what I want to do is run more trials down there just to see quite how good it is, because it might not be the best. So I have this kind of coupled, this trade-off. I want to be able to balance the time I spend exploiting versus exploring. And because this is a tree search algorithm, I want to do that at multiple levels in the tree. Because I need to really, because I'm building this tree online, I want to expand the tree as much as possible, but not really beyond looking in the good areas of the tree. So one way you can think about this algorithm, in some sense, it's sort of focusing effort on the bits of your tree that are likely to contain good solutions, which is similar to how A star works, but here we're doing it purely in samples and purely without a model. So you can think about this minimization as, with just the Q value, as exploit. So we're going to put in an exploration term, and we're going to use this extra bit of maths on the end, which we're going to take away from this. So this minimization is over the whole thing, which is we're going to minimize this minus some constant, and then we're going to take the square root of the natural log of the number of times that we've visited the state, and we divide it by the number of times we've taken this action in this state. So these state and actions are the ones up here. And this means basically the more times we've taken it, the smaller amount we're subtracting. And that means the actions we've taken more, we want to explore less. Okay. So actions that are we've visited less get kind of a bigger bonus because we're minimizing. And so this is the way of balancing exploration and exploitation. And this is called, let's go to a third color. So this bit here is actually from an upper confidence bound. So you can think about this, effectively there's some variance in the distribution that we've got for our Q value. And this is a way of capturing how wide that distribution is, kind of the variance of it. And this UCB was taken from a bandit algorithm. The algorithm we've got is called UCT, where T is tree, because we're applying this in a tree search.
When you say bandit, is that like a fruit machine?
Yeah, so people use bandits to think about if I've got a choice to make, and I don't know how good each individual choice is, I think about this as multiple bandits. So I've got like a bunch of fruit machines in front of me, and I don't know which ones. I've got £1. Which one do I use? Well, I want to use the one that's going to give me more, that has a higher chance of giving me more money, or that gives me more money, or combines both. And the way to think about that, so a bandit problem is like I've got, let's say, an infinite number of pounds, but I have to keep trying the bandits to learn the distributions of the rewards I get back. And the kind of Bayes optimal way, probably Bayes optimal way, or one common way of doing it is using this UCB algorithm, which is effectively you select the one that has, you select ones based on the mean plus the upper bound of a confidence interval, or the upper bound of the variance. And if you do that, you typically choose ones that have high value or have high variance. Okay. And ideally, over time, those things kind of, the variance gets washed out and you only choose high ones. But we're applying that to trees, but we're doing it with the same action. So I typically want to choose actions that have high value or high variance, because I want to reduce that variance. And if that's got high variance, that means it could have a high value. I just don't know it yet. And this kind of collapses it all into one number that we can minimize. So in the bandit, I was talking about maximizing. In the actions, we're minimizing cost. This is a minimization problem. Key idea, maybe just the thing to go back to, explore is this bit, because it's kind of valuing things we haven't visited much. Exploit is this bit, which is valuing things that look good. So we go back to our tree. And we've started here. Now all of that description is actually kind of pointless, because at the start, I haven't run any trials, I haven't chosen any actions. And so the denominator on that fraction is 0 in all cases, which means the exploration term is infinity. So all of those actions look amazing. And what you're typically forced to do is try all actions once. So we're only going to really come back to that later on when we've got a choice between actions. What we're going to do is we're going to try all our actions once, and we're going to do that in alphabetical order. What we're going to do is add our first action. So we've got two types of nodes. Decision nodes. Decision nodes are where we need to make a decision about what action, and they're circles. Chance nodes are nodes where we get some randomness. Those are the outcomes of the actions. Here's going to be my action, and we'll just have a Q value because it's an action. So it's the Q value of being in H and taking the bike. And so this is our expansion step. We've expanded the tree by adding this new node, and now we have to initialize. How good is this? Well, the way we work out how good things are in our sample-based approach is by doing simulation. So the previous thing said simulation. The way we do simulation is we combine random sampling in the tree with our sampler, and we need something called a rollout policy. So the rollout policy takes the trial through the tree to the goal and just picks things without knowing what the best thing to pick is. And a typical thing to use is a random policy that randomly picks actions. And this is all going to happen kind of outside of the tree. And we're going to use the information from that to pass values back into the tree just to initialize them. So this is really the initialization step. And over time, as we put more samples through our tree, we're going to get more information and kind of grow the tree and learn more. So what we're going to do here is we're going to roll out down the tree. We can think of this as kind of some random process happening. We actually know that the bike action is deterministic. It reaches the goal. So we roll out to the bottom of the tree and it costs 45. So effectively, this policy runs. We simulate the behavior of our search algorithm or our agent down the tree, and we get a value of 45 back. So what we'll say is that we know at this point, bike costs 45, because that's what our random rollout says. And we can also count how many times we've done it. So we've done this action once. So we can throw away our rollout. So up here, we will set the value of the tree of this node to 45, because we're minimizing over all the other actions, and we've only got one action. So we will set that to 45. And we also really need to keep track of how many times we've visited this node as well. So let's do that again. We're being forced to choose all of our actions. So this time we're going to choose car. So here we've got a Q value of being in home and car and how many times we're doing it. And once again, we're going to roll out. And the rollout for the car, if you remember, well, we first got the cost of the car. So getting into the car costs 1. And then we visit some traffic. And if you remember, there was like 20% of the time we got low, 70% medium, and 10% high. So it's most likely, if I'm sort of simulating this in a lazy fashion, that we're going to hit the medium traffic. And the medium traffic costs 30 to get to work. And there's no action choices here. So even though I've got a random policy, there's only one action to choose, which is to drive. So I reach my goal, which is being at work. And then we can back up to here, the value from the rollout, which was 31. And again, we can update our count. And then at the top, we've now run 2 trials. So our count through the top is 2. And actually, we can change our value to 31 because we've got a lower value we're minimizing. And we go one more time, take our train action, walk to the station, and we initialize these things, empty, and then we roll out one more time. Probably should just keep this on the table at this point. So it costs 2 to get to the station. So that's our first action. That's the cost of this action, really. And then the outcome state is either we land in the train, or the train isn't there and we land in the waiting. And it's like 90% of the time we land in the train. So we're going to assume that happens. And then it cost me 35. So we land in the train and we relax to work and we get to work. So that costs 37 and we get back to here. And we don't need to update our value up here because 31 is still better. And we've got to 3 trials. So at this point, hopefully you're getting a bit of a sense of what's happening. We're running some random trials. That's giving us some values. Our model is super simple. So these values already are kind of pretty close to what we know their optimal values to be. In fact, we know the bike is because there's no randomness. And there's some finessing to do around here, but because we've got very high probability outcomes in the random parts underneath, or in the stochastic parts underneath, we can do all right. So we're on to trial 4 now, and I am going to use some of my previously done calculations to show you this. So what we've got here, we're now in this trial. We've got the values of our actions, and in our selection step, we need to know where to send our trial. So these values here are the results of the UCT calculation. And it's actually a bit of a cheat. They're not so important now because the ends are the same, right? We tried each action once, then effectively the right-hand side, the exploration term, is constant for all of these. Therefore, really what we're doing is selecting the lowest action still. So that is going to be our car. So we're going to run our 4th trial by choosing to go to the car. And what we're going to do is we're going to simulate again. And just for convenience, let's just assume we get the same rollout. So save me writing another bit of paper. We get medium again. And that's useful because the 31 doesn't change, because 31 is the value of that in our rollout. We just need to update our counts here and our counts here. So this is when things will start getting interesting and the UCT formula will start influencing our behavior. So we now go up to our next trial, which is one in the middle. We've got our different counts. So this is the NSA, the number of times we've taken the action in the state. We've got our values, which are unchanged from before. But now, because the total number, and we've got some differences, we get some differences over here, and we can see that the lowest value is actually rail. So this is where the exploration part is actually coming in. So if we just looked at the Q values, we'd continue to pick car. But now the UCT formula says, well, actually, we need to explore a little better in the rail angle, because the way to think about this is the values are kind of close. And this one is, we haven't visited it as much, so we want to go and look there. So we'll roll out our train. And okay, so it takes 2 to get to the train. And this time, let's assume that we end up in the waiting room. So we're not on the train. And at that point, we have an action choice. We can either choose to wait or we can choose to go home. At this point, what we'll do, we might make a random choice. So this is where our rollout policy would come in. We need to actually make a decision in the tree as part of the rollout process. Let's assume we wait. I mean, we could fix it. We'll assume we wait. So waiting costs another 3. 3 seconds of waiting, and then let's assume the train comes, but we might need to loop this bit randomly a few times. We roll to get to our goal, and I think in total, the number to back up will be 40, because the sum of that, because there's a 35 down here. And so we take this back, and now this is where we're doing the Monte Carlo step. So we've now got 2 cases here, and we're effectively taking an average of the previous values. So what we did we did that previously, but because the values are the same, we didn't really do the maths. And here, there's not a lot of maths to do. We do 37 add 40, and then divide that by 2, because we've been through twice. And that gives us, I think, 38.5, which is our new value for this node. The other thing that we should have done, and we probably should have done it earlier, but let's just do it here, is because we sampled from this node now, we initialized this last time we visited it. The second time we visited it, when we ran our action, we're actually able to add a new expansion step. So we actually missed, on the previous one, we missed the expansion step, but it's fine because we can talk it through here. So the expansion step here would have been to take us to, if we did it on this time, it took us to the waiting room. And so our waiting room, we will have initialized with the value that we got. So we actually visited this once, and we initialized our value to being in the waiting room. So that is 38. Because going to the train costs 2, so this would be our value of 38. So when we visited, because we'd visited this once, we were allowed to expand below it. So we would have done the same. I can go back in time. We would have done the same here, and we would have got, I think, medium traffic, which we would have initialized to 30, because on the second time in, we can expand it one further. So this gives you a sense that we're growing the tree down, and we're slowly updating our values. So you can see the value here changed because we got a different sample from our tree. And that's kind of the property of these Monte Carlo or sample-based algorithms. We're going to update our value as we go. The value of the root node and the best action is unchanged.
Do you have another 1 on here?
Definitely have another 1 on there, because now we've done 1, 2, 3, 4, 5. So we've now done 5 trials through there. And if you carry on doing this, you'll find that the UCT term forces you to sort of distribute your trials across these actions. And then as you go down, you'll do the same. So you'll end up having choices under the wait between going home and staying in the waiting room. And so that will also have the same kind of properties. We'll need to make choices. We'll need to explore the values of staying and waiting. And what becomes a bit interesting there is we actually get a very deep tree, because there's a potentially infinite loop here, and that will add depth to our tree. But in general, after a while, it will become quite clear that car will be minimizing our choices, so we won't explore too deep in that tree. One interesting part, we mentioned this at the beginning, you've got a variable thinking time. So typically we're going to run this algorithm as the robot maybe is driving to the next state, when maybe it knows where it's getting to, or maybe it's sitting there thinking. And you might want to interrupt it quickly. There's no guarantee with this algorithm when you interrupt it that you've got the best action or even a good action. Because if I've got some very kind of low probability samples, I'm not representing the distribution or the values very well. So we're trying to kind of approximate expected values. We're doing that via samples. For very low sample regimes, that value can be very inaccurate. And so if I'd actually, when I'd taken the car, if I was unlucky and I hit the high traffic load, then this action would be 70 or 71, and that's kind of double what that's getting, it's double what that's getting. And so we'd have to take a large number of samples before we even try the car again. And if we'd interrupted before that, we wouldn't take the car, and that would be the wrong choice. And then it's a random algorithm, right? It's not only, the model it has probabilities in it, the algorithm is random as well. There's a few things to say, like one of the ways people deal with that is they typically run a bunch of these in parallel, and then let each instance vote on what they think the right choice is. And that's maybe, there's a few other kind of caveat, like this is just gonna be additional detail. I sort of haven't been very specific about how we're using this. We typically only take the one action from the tree. So we run this, we take the best action, so the lowest Q value, we execute that, and then we run again. So you often would phrase this as online planning, or some people think of it as receding horizon control. So when I'm thinking to my goal, but I'm only executing the next action. The reason you do this is as you get further down the tree, the values get less and less accurate. So you've done a decent job of characterizing the values higher up, lower down they're noisier. So you kind of trust up here. And then when you do that kind of parallel process, they're all just kind of voting on actions at the first level. And that kind of washes out a bit of this kind of bias of the bad initializations. There's one thing I didn't say, sorry, which is just to go back to this. And I put this constant in here, and then I did some maths, and I didn't explain what that constant was. So the UCB, I can't remember if it's the UCT or the UC, I think the UCT paper says there's like a specific value for this constant which minimizes what's called regret. Regret is the difference between the choice you're making now and the choice you would make if you had full information. So if I knew the optimal choice, the optimal action to take here, how bad would the difference between that and the choice I'm making now be? If you use that constant, the exploration is very conservative. You tend to spend a lot of time exploring and not a lot of time exploiting, which means for practical problems, you don't make very much progress. The kind of typical thing we do is we actually we replace that with the value of the state that we're looking at. The advantage of that is it makes this side comparable in value to the other element of the equation, which means you see more of an effect from the exploration. It allows you to kind of put these things in the same terms, and you don't get completely washed out by bad samples. In the medium traffic state, it cost me 30. And that's why if you look back to this function, it's both kind of an S and an A in the cost function. It's like, okay, I'm executing this action, which might be drive, and then this could be light traffic, LT. This is a decision-making model. What we want is